Hello, my name's Duncan and welcome to one of my hot takes. This hot take is about potentially calculating the factor of safety for component parts of trees. Let's have a look. So quickly, I need to define what factors of safety are. This concept comes out of structural engineering. The essence of it is about asking the question, how much stronger is the structure than the service load that it has to take? So for example, a bridge has been designed for carrying a maximum of 20 heavy trucks at any one time. Well, it may have a factor of safety built in of 3. So it could just about carry 60 heavy trucks, 20 trucks times a factor of safety of 3, before it would broke. The reason an engineer might do this and add factors of safety is to ensure the safety of users and anyone associated with the bridge, to take into account accidents or inclement weather or material deterioration of the things the bridge is made of. The difference between the factor of safety and the service load is known as the margin of safety. So for this imaginary bridge example, then the factor of safety is 3, then the margin of safety is 2. Or put more simply, the bridge can take up to 40 more trucks than its usual loading of 20 trucks, and just about not fail. There are different standards to factors of safety depending on the purpose of the structure, what forces may apply to it, the risks involved, and similar considerations. As shown in the 3 equations on this slide, engineers recognise different equations for the factor of safety for brittle materials and ductile materials. The wood of trees is not brittle nor ductile, so the more general equation at the top of the list on the slide is considered sufficient by most authors. Although the anatomy and functioning of component parts of trees is complex, there would be considerable benefit if we took this approach to attempt to estimate, or better to calculate, the factor of safety of component parts of trees and how much that factor of safety may be lowered by the presence of a structural defect. In fact, the concept really helps to separate out what is a feature on a tree, such as a gall or a canker, from a defect, as a structural defect will measurably lower that part of the tree's factor of safety, let's say by at least 5%. A feature would not be having that influence on the tree's structure. It would be great to know the factor of safety for component parts of trees, but unfortunately, unlike engineering books of materials, where such figures are given for many engineering items, the factor of safety book on trees is yet to be written. And that is because calculating the factor of safety of just one scenario involving a tree is complex. To start with, one needs to be able to determine the service load to that part of the tree with confidence. This can greatly vary depending on the location of the tree, its form, the nature of the wood in that location, and how we might try to calculate what is typical loading. Most authors on this topic, such as Carl Nicholas, have sought to annualize the loading using the typical maximum loading to a tree structure, which is most often, in the UK at least, during autumn and winter storms. Ideally, the typical maximum loading, the typical annual maximum loading, would be measured rather than estimated, because calculating the wind drag of a tree is also very complex and beyond most computer simulators to achieve with any degree of accuracy. Then comes the additional problem of the fact that a tree is alive and growing, unlike the concrete and steel structures that engineers typically get to assess. This means that tree growth, informed by the process of thigmomorphogenesis, can act to strengthen a weakened component part of a tree's structure. In general, such strengthening is more rapid in young trees that are growing well, and it can be tortuously slow in late mature trees where growth is now going at a very slow pace. The image on this slide shows one of my photographic time lapses of a tree. In this case, the subject of interest is a bark-included junction in a silver birch tree. Over 15 years, you can see that wood has been added such that a large linear bulge has developed, covering up much of the bark inclusion to form what I have defined as a cup union. It is tempting to say, with this additional wood being added at this branch junction, that this component part will have improved its factor of safety over these last 15 years. However, one must also take into account that the tree has grown taller and that the two limbs attached together at this junction have got heavier. So it would be possible through carrying out experiments to be able to say something like this. This junction used to have a factor of safety of 2.7 in year X, and now it has a factor of safety of 3.1 in year Y. But it would take a lot of effort for the one junction to do this, and the experiment necessarily would be a destructive one. In my PhD studies on the biomechanics of branch junctions in hazel, Corylus avellana, as I had tested over 400 branch junctions and had measured the movement of such trees using accelerometers, it was possible to put some estimated factor of safety numbers down for that component part for branch junctions in hazels. A normally formed junction would have a factor of safety of 4 to 5, a cup union between 3 to 5, a bark-included junction with little modification, so not much bulging, would have a factor of safety of about 2, and a cracked branch junction would have a factor of safety of about 1, or essentially no margin of safety. It's very likely, however, that factor of safety varies also due to the tree species involved. If you've managed trees for many years, you'll know that the species of tree in your region, you'll know the ones that are more prone to shedding branches or collapsing in storms. Where I live, it's willows and white poplars that would be high on my list in Lancashire, England. And you would also have some experience of much more wind-firm trees, such as yew trees and Scots pine trees where I live, although Scots pine will shed the occasional branch. It is likely that, even if all other factors were equal, that the species of tree causes a variation in the factor of safety. My guess at the range of a factor of safety of about 3 for some willow species to a factor of safety of up to 8 maybe for something like a yew tree or a hornbeam. There is even the potential for a component part in one species to have a relatively lower factor of safety than in another species, which is why we might say that species A is prone to stem breakage and species B is prone to branch junction breakage. The only way forward here is for more scientific work to be done, testing the mechanics of trees, carrying out storm damage surveys and cohort studies that involve structural failures, and looking to fill in the many gaps in our knowledge. This would require a lot of repetitive work until patterns of biomechanical behavior can be discerned sufficiently by species, but would really help us to assess tree structures, so perhaps putting in those many years of study would be worthwhile. It's important to point out here what science is capable of and what it is not. If you get the average, or I like to say the mean, factor of safety of a birch tree stem from the extensive experiments, even the typical variation within a birch population of that factor of safety for a birch stem, it does not mean that the single birch stem you're assessing has that average factor of safety. Science can pick out the mean value. It can't account very well for individuals. This is like saying, if you smoke 10 cigarettes a day, you've increased your risk of getting lung cancer by 10%. But it doesn't mean that a particular individual that smokes 10 cigarettes is going to get lung cancer. It's only a typical value. It's a mean. It's an average. So, what have we learnt? There is no doubt that an arborist and arboriculturist would be paid more if they could put meaningful figures to the tree structures they're assessing. It would certainly be a much more professional approach than we are capable of currently doing, which is based mostly on experience with trees, anecdotal evidence, and a little bit of valid science to support our decision making. If we are to calculate the factor of safety of tree component parts, well, we've got a long way to go. The two images here are again more of my time lapses, one of a tree that failed and one of a tree that has persisted. In the former, a beech tree with root decay and a lean has fallen in a low-level summer storm. If a root investigation had been undertaken, the much lower factor of safety could have probably been detected by finding rotting roots at the tree's base. even if the factor of safety was not quantified accurately, you could still get a good idea that the factor of safety had been reduced. However, for the second time lapse of a split fork in a cherry tree, who would have predicted that this component part would have persisted intact for 13 years? Well, there are a few aspects that would help with explaining this. The first tree, the mature beech tree, was fully exposed to a prevailing wind, and the root rot it had was progressive. The second tree is on the leeward side of a shelter belt, sheltered from the wind, and the tree has been adding wood around that junction since it split, improving its factor of safety over time, most probably. Examples like these hopefully show how factors of safety could be applicable to our practice, but several other factors need to be taken into account, especially the extent of wind exposure to the tree and its growth rate and means of resources for recovery. Which leads me to my last point on this rather long hot take. Even if we have done all the work needed to predict accurately the factor of safety of any component part of any species of tree, so hundreds of years of work by many scientists, how much is it typically going to reduce by a range of defects? There will still be a major unpredictable factor in undertaking our predictions. The nature of the weather, especially wind and rain, and their strength and direction, is an important factor as to whether parts of trees fail, and the weather is always going to be unpredictable. So again, we could only base our judgments on typical weather that happens each year, or estimate whether weather conditions might cause or assess trees to fail. Thanks for listening to this hot take, and I hope you enjoyed it. Talk again soon.